This is something that one of my favorite, SVM. Okay, let's see what SVM is. It's another linear classifier. It's a linear classifier, and number of categories and class. If we have 2, that's a binary, and more than 2 is a multi-class. And again, we're gonna start binary case because that's the simplest case. And because in the previous one, I said that we want to utilize the distance informations for the optimization process. So we guys already know how to compute the distance from line. So x, whenever x and this given, we know that we already did that. So omega is perpendicular, and sine the distance we know how to compute. And the distance, this is something that you guys are supposed to remember and memorize it. That's the distance. I'm gonna use that later on. And let me think about, so we know that h is g of x and divided by, and this one is g of x is equal to 1. I mean equal to 0. So all the data points, we have a straight line. And what do you think? If g of x is equal to 1, what will be if you have all the data points that satisfy this constraint? And from this, we know that if any x that satisfy this, that means h is g of x divided by omegas and is 1, right? Any x is distance is 1. That means like this one. I mean distance is 1 over. So that's the distance. And what about and that's the distance. And we do have sine, that's why in the opposite directions. And all of them have omegas like that. All of them are perpendicular. So suppose this is g over x equal to 0. And say omega is in that directions. Then we know that this one is omega is 1, and here is -1, and distance is -1, and distance is 1 over and positive. That's something like you should like understand from scratch. Right? Using this in your mind, let's move on to then another method to find out distance between these two. What's the distance between these two? I mean, we know that from distance from that and distance from that is 1 over, and 1, I don't know which one is that, but we say that this is minus, then the distance between these two probably like that. That's how we can compute from the previous one. And what I'm asking is that what's the distance these two? And suppose we have x of 1, x of 2 satisfy this its equation. And x of 1 is like that. I mean, I picked random or any point, arbitrary point, and x of 2 is, and s is the distance that we want to compute out of it. And we know that the omega is in that directions, and omega naught plus x of 1, omega transpose x of 1 is -1. And here omega naught plus omega transpose x of 2 is 1. And if you say take the minus like that, and omega transpose x of 2, x of 1 equal 2. I mean, equal 2. And we know that x, so we got that one. And let me compute inner product. Let me compute the inner product. Let me see. That's if you, this one is unit vectors, and if that is, I mean, say x, this is the vectors, and omega is in that direction. This is the inner product. S is omega transpose x2 minus x of 1. We know that this is 2. So that's the distance of S. I mean, there's no additional information, same as the one that I explained the previous, but there said I'm going to introduce or show you another method. Okay. So now let's think about the binary classification problems as a to see what SVM is. And binary classification, suppose we have two classes, it's C of naught and C of 1. And again, it's two-dimensional space. And we can discuss it in higher dimensions, but in two dimensions is the simplest. I mean, you can easily visualize and draw. So we have two coordinates. Let me see. Is it possible to distinguish these two, its coordinate on the map? We need to find the separating hyperplanes, yes, as a classification boundaries. In 2D, it's going to be the line. And the linear boundary classifier is like that. I mean, we already did that in perceptron. And we can formulate it like that in vector form and like this. Decision-making process. X, we have X says given data points, we know that it's whether it's belong to the C1 or C naught. That means we want to find out the omega naught and omegas to satisfy all data points that belongs to C of 1 should be positive. All the other class should be negative. If we are able to find omega naught and omega 1 satisfy this, then it would be like good linear classifier. Same as perceptron. And find out omegas and omega naught such that like this. Again, eventually, like data points here and another data points, we're going to find out this. linear classifiers. The motivations or the purpose of linear classifier same as the perceptron. Now let's go further. This is or let me, we find out omega and omega naught such that all the data points here is, instead of 0, we can +1 or -1. This one might be like confusing, but let me show you that one. If that's the, if we are able to find some of linear classifier, then we know that suppose the omega is in that directions, and if that's the, and this one will be g of x is -b. What's the distance over there? What's the distance? It's b divided by omegas. So there, -b divided by omegas. If we are able to find any linear classification boundaries, that means the data points are linearly separable. So we have two groups of data, right? And suppose we can find out, then I can, like that, until that I reach that point. Like starting from that, and I'm gonna keep increasing it and decreasing it like that until these two lines are touch, like each data points in each group. So that's why I said instead of find out the decision boundaries, I want to find out decision band. That's the key idea of SVM. SVM. So B exists always, positive B. If that's data is linearly separable, and we can find out -b for C1 and for C naught. And these are the unknowns, omega naught and omegas. And we can divide by b's, because since b is positive, then we can divide it omega naught divided by b, omega transpose divided by b, x is equal to 1. And in that case, omega naught minus b, x is -1. I mean, these are the unknowns, and divide by b's, it doesn't matter. So another omegas, like omega naught prime and omega primes, because always we can normalize or divide by b, doesn't matter. So the problem for SVM, we want to find out this, instead of finding the decision boundary, we want to find out decision band, and on the right side is 1 or -1. Because if we have non-zeros, we can divide by. Okay. Now let's see. I generate the data points. All the data is, let me see, is C1 and like, I would say blue and red. Let me see, let's formulate it in the SVM problems or classification problems. And we have two features. I mean, we have two, like x1 and x2, and n data points in the other group. We have in total, we have m, small m data points in the training set. Okay. And actually there are two representations. And if you do have this way, then we have omega 1 and omega 2. So in that case, it's like x omega transpose omega not equal to 0. And if we have x of 1, x of 2, either 1 or x naught, then omega naught, omega 1, omega 2. So in that case, x transpose omega is equal to 0. I mean, just same, but if we have different, then in vector form, we might have. So I'm going to show you both at the same time because they are the same. And in optimization problems, we want to find out these because this is going to be unknown variables, decision variables. So let's move on to how do you model it. How do you model it? We have n data points we already know. That should be, all of them are +1, greater than +1. And n data points like that. In these notations, we have omega naught, but in other we have it's like that because. And what about the objective functions? We don't have any. These are the constraints. As long as the data points for each as satisfy the boundary, I mean the inequalities, we're happy about it. So we don't have to do any, we don't have any objective functions to minimize. Good. You see what I'm doing it? So we have these two groups of data points, and probably this is C1 and C0. And we hope that with right value of omega naught and omega, those are decision variables that we need to decide, we need to find out of optimization problem, such that subject to satisfy these. If the data set is linearly separable. And there's no objective functions to minimize. So the good thing is that we do have CBX pi. And we minimize something, so we don't have any. So I say it's a minimize 1, because that means doesn't do anything. But we do have constraint like this, and ask to solve. And I want to see what kind of value of omegas. And this is what we got out of CBX, which is good, right? Because it's a good linear boundaries. So this is the models for optimization problems. Model of optimization problem for binary classifications, and we implemented in the CBX pi, and we got one of them. Then let me ask, what if we have outliers? That, which means that I intentionally introduce these data points to make it the data set is not linearly separable. And this one is not linearly separable. We cannot have any straight lines to have, so we cannot. That means out of this, the solution does not exist. Like a perceptron. I mean, this is same as perceptron, does not exist. That's the problem. I mean, for computer, say that since this data points, we're not able to. But if I ask you guys with this data points, draw the straight lines, you guys know that probably you will do like this. We might have some misclassified data points, but it's okay because it's just few of them. I think we, like humans, we do classify even though we have some outliers. But if we ask the computers, they cannot. Only thing that we learn is that they're gonna do something when the data set is linearly separable. That's the problem. That's the issue that we have. So we want to have something, some kind of classification method is more robust that we can do something even though we have some misclassified data points or outliers, like what we do. That's the biggest challenge that we have at this moment. That's the biggest challenge that we have. So no solution exists. So we cannot stop here. We have to do something. We have to do something. So the idea is that we have to allow some training examples or data points to be misclassified. Like this. We have to allow some of the mistakes. If we do, then probably like this will be another solution, but we don't want to have that. So at the same time, we want their number, which means the misclassified numbers, to be minimized. That's the key. We want to allow some of the data points to be misclassified, but we want to minimize that. Again, it's optimization, another optimization problems. Having this kind of things, probably in that case, we might have that. That's the ideas. That's the key idea of SVM, right? It's going to be more robust if we are able to implement this. If we are come up with some good ideas or method, say that we won't have some kind of linear classifiers even for the non-linearly separable data set. Okay, that's the motivation for SVM. I will stop here, and next time I'm going to show you how to implement these things. This is extremely smart. I'm saying that. So that's the key idea of how we implement these ideas. Allow and minimize that. Okay, and I'm gonna stop here and let me